Hello again, and welcome to our second lecture on logarithmic functions. I hope you found the last couple of lectures on exponential functions and logarithmic functions interesting and yet challenging. I'm the first to admit that logarithms, it's not an easy topic in mathematics. You'll recall that we defined the logarithmic function as the inverse of the exponential function. And in today's lecture, I'd like to spend some time exploring the properties of the logarithmic function. But before we get started, let's review the definition of the logarithmic function. Recall that the domain is x bigger than 0, and the base is a number a also bigger than 0 and not equal to 1. And then we define y equals the logarithm base a of x to be equal to y if and only if x equals a to the y. You see how that inverse property works. The logarithm is defined in terms of the equivalent exponential function. And this function, f of x equal log base a of x, is called the logarithmic function with base a. And of all the bases, two of them stand out as being the most important. Base 10 logarithms, developed because basically we have 10 fingers and we count in a base 10 number system. And then we saw last time that base e logarithm, which was the inverse of the exponential function e to the x. So those are the two important bases. Well, always keep in mind also the graphs of y equals e to the x and y equal the natural logarithmic function. These graphs are mirror images of each other across the line y equals x. Please memorize these graphs. They occur over and over again in mathematics and science and engineering. Notice that the graph of e to the x has a domain, all real numbers. That means that the range of the logarithmic function is all real numbers. The domain and the range interchange each other when you go from one function to its inverse. Okay, good. What happens, though, if you're doing a problem and you're dealing with a logarithm to a base that's not 10 or not e? So you look on your calculator and you go, uh-oh, I only see two log buttons on my calculator. There's log base 10 and there's log base e. What do I do? Well, fortunately, there's a formula for converting logarithms to any base using the quotient of logarithms either to base 10 or to base e. Let me show you that formula. The logarithm to base a of x is given by the quotient of log base 10 of x divided by log base 10 of the base a. Or you could do it as natural logarithms. So the log of x to base a is equal to the natural log of x divided by the natural log of a. So it's a very convenient formula. Let's use it in a couple of examples. Suppose you had to find the logarithm of 25, but to base 4. And again, logarithms to base 4 are not on your calculator. So you've got to use this formula. So here's how you could do it. One way would be write it as log base 10 of 25 divided by log base 10 of 4. And then those you can calculate on your calculator. As approximations, the log base 10 of 25 is about 1.39794, and the log base 10 of 4 is about 0.60206, and that quotient comes out to be about 2.32. Now, you could also do it a different way. You could say the log of 25 base 4 is equal to the natural log of 25 divided by the natural log of the base 4. And now you get different numbers in the quotient. You get 3.21888 approximately in the numerator and 1.38629 in the denominator. But fortunately, that quotient comes out to be the same. Thank goodness. The answer again is about 2.32. And I invite you to do the following when you have a free moment. Pick any old logarithm to base 7, say, and calculate it using both of these formulas, the log base 10 or the log base e. and see if you get the same answer like we did here. Okay, good. I'd like to now enter or look at some of the really important properties of logarithms. These are the properties that historically were used and motivated the development of logarithms. These are crucial properties for calculus courses and for the rest of our applications of logarithms that are coming up. The bottom line is logarithms are very good at converting products to sums, and equivalently converting quotients to differences. Again, this is one of the original uses of logarithms. Let me show you one of those formulas. The logarithm to base a of a product, say u times v, equals the sum of two logarithms, the log base a of u plus the log base a of v. So you see that the log of a product is the sum of the logarithms. And by the way, this is how slide rules work. Here's a slide rule that I brought in. I used a slide rule when I was a student in college. We didn't have calculators then. And when we often had to do multiplication problems, the slide rule would convert those to addition problems. It was kind of a magic tool that we used. And then along came the calculator, and slide rules became obsolete. Kind of sad. Okay. Students often ask me, okay, professor, you gave me this rule that the log of a product is the sum of the logarithms. How come that's true? Convince me that that's a real formula. Well, let me try to do it for you. Now we're going to do what we call a proof in mathematics, so don't panic. Let's try to convince ourselves why the log of a product is the sum of the individual logarithms. And the idea here is using the inverse properties of logarithms and exponential functions, we convert that problem to an exponential problem. Watch how it goes. Let's let x be the log base a of u, and that's equivalent to saying that a to the x equals u. And let's let y be log base a of v, and that's equivalent to saying a to the y equals v. So I'm converting the logarithm equation over to an exponential equation. So what's a to the x times a to the y? That would just be u times v. But now wait, remember that property of exponents? If you have a to the x times a to the y, you add the exponents, don't you? So now we have the equation a to the x plus y equals uv. That's an exponential equation. Convert it back to a logarithmic equation. It would be log base a of the quantity uv, the product uv, equals x plus y. And lo and behold, what's x? Oh, x is log base a of u. What's y? Log base a of v. And bingo, we've proven it. Congratulations, you did a mathematical proof. Now, there are two other properties that are equally as important, so let me summarize all three of them. The one we just showed and we actually proved is the log of a product is the sum of the logarithms. The comparable property is the log of a quotient is the difference of the logarithms. And a third property that looks a lot different, but equally as important, the log of u to a power, u to the n, say, is equal to n log u. And of course, these logarithms are all to the same base, a. Notice that third property. What that says is, if you see u to the n, u to some power, you can motor that power down in front of the logarithm. That's one of the key powers of logarithms. Things that are hiding up as exponents can be pulled down in front. We'll use that skill over and over again in today's lecture and the next lecture. And by the way, of course, these properties hold for natural logarithms when the base is e. Let's do some examples. Let's play with these formulas a little bit. Can you simplify log 2 plus log 3? And here I'm using, say, the natural logarithm. So the natural logarithm of 2 plus the natural logarithm of 3. Well, that's the sum of logarithms, and it's equal to the logarithm of their product. So it's the log of 2 times 3, or log 6. check that on your calculator tonight. Punch in log 2, add it to log 3, and then compare it to log 6. You'll get the same answer. Here's another problem. Log of 2 divided by 27. Can we simplify this or write it in a different way? Well, that's log of a quotient. That's going to be equal to log of 2 minus the log of 27. And again, you could check it on your calculator. Here's the third problem. Log base 6 of 6 cubed. Well, remember that third property I just talked about? That 3 hiding up there as an exponent can motor down and be put in front of the logarithm. So it's the same as 3 log of 6 to base 6. And we remember that log base 6 of 6 is nothing more than 1. And so the final answer is 3 times 1, or 3. Of course, we knew that property earlier, didn't we? We could have calculated that earlier without this fancy formula because, look, these are inverses of each other. 6 to the cube, 6 to the third power, is the exponential function, and then we log that. They're inverses, they undo each other, and you're left with 3. But let me show you one that's not so easy. How about log base 10 of 49? Can we simplify this? Well, 49 is 7 squared. So this would be log base 10 of 7 squared. And now that 2 can be put into the front. It can slide over to the front, and you have a different form of the expression. It's now 2 times log base 10 of 7. Okay, a warning, bad news, sad news. The logarithm of a sum is not the sum of the logarithms. The property is the log of a product. By the way, I see this error all the time. And it's the kind of error that I think people just sort of forget. But it's kind of sad that this is not true. The log of the sum of two things is not going to be the sum of their logarithms. It's just, it's a false formula. But it's a common mistake that we all make. Okay. Let's do some more examples, a little bit more interesting, a little bit harder. Here's an expression. Can we take this complicated expression and write it as a sum and difference? How about log base 4 of 5x cubed y? So it's the logarithm of the quantity 5x cubed y. That's a product. In fact, it's a product of 3 terms, so I can write it as log base 4 of 5 plus log base 4 of x cubed plus log base 4 of y. Good, I've broken it into 3 pieces. But I can do more, can't I? Look, that x cubed, I can bring the 3 down into the front. So another version would be log base 4 of 5 plus 3 log base 4 of x plus log base 4 of y. Here's another expression, actually from a calculus book. Log of the square root of 3x minus 5 divided by 7. So it's the logarithm of a quotient, and within that quotient, you've got a square root. Can we simplify this? Well, first of all, notice that a square root means it's an exponent of 1/2. So this is the natural log of 3x minus 5 raised to the 1/2 power divided by 7. Now it's a quotient, isn't it? So it's the difference of the 2 terms. So it's log of 3x minus 5 to the 1/2 minus log of the denominator, log 7. Okay, can we do more? Yeah, that 1/2 can motor into the front, and we get 1/2 log 3x minus 5 minus log 7. You might notice that I say log, sometimes I say natural log, sometimes I say log base A. The bottom line is, in the context of the problem, you'll know what base we're dealing with. It's as long as the same base throughout the problem. Now, this is a pre-calculus course, and hence topics that we're covering are important for calculus. And these logarithmic properties, I can't emphasize enough how important they are in calculus courses. The idea of expressing a product as a summation is really, really important. Let me give you a taste of that. There's an activity, there's an operation in calculus called the derivative. And It's easy to calculate the derivative of a sum. You have to trust me on this, whatever a derivative is. But it's easy to calculate the derivative of a sum of functions. It's very complicated to calculate the derivative of a product. And so logarithms play an important role in taking products and chopping them into sums, and then you can find the derivative of that sum. If you have a calculus book, look up the topic logarithmic differentiation in the index, and you'll see what I'm talking about. And in fact, this was one of the original uses of logarithms. Okay, some warnings, some pitfalls. And this is really an interesting pitfall. This is one you can do on your graphing calculator, and you'll be kind of amazed. Remember that the domain of the logarithmic function is all x bigger than 0. And this comes into play sometimes. Consider the following two functions. One of them will be the log of x squared, and the other one will be 2 log x. So you might graph these on your calculator. y1, your first function, would be log of x squared, and the second function would be 2 log x. In a sense, we've used that property, haven't we, of moving the 2 down into the front. But now wait. Think of the domains of these two functions. What's the domain of log of the quantity x squared? Well, because x squared is positive except for 0, the domain of that function is all x except for 0. But what about that second function, 2 log x? Aha! Its domain is just x greater than 0. So that property that I mentioned a few minutes ago about moving the exponent down into the front, you have to be careful because sometimes you change the domain of the problem. So try graphing these two on your calculator. You'll see that the graphs coincide when x is positive, but not when x is negative. Here's another pitfall that I've bumped into a few times as a teacher, and it's a notational pitfall. The expression log x, and you put parentheses around the whole thing, to the nth power, that's not equal to n log x. The correct property is log of x to the n, where the parentheses are around the x to the n. And then you can move the n into the front. For instance, log of 2 to the 5th is the same as 5 log 2. That's true. But log of 2 all to the 5th power, the entire log is to the 5th power, that's not 5 log 2. So be a little careful there. Now, I mentioned that logarithms are really important in applications. Let me just mention a couple of areas of science that you might have seen logarithms when you were studying these fields. I used to be a chemistry major, actually, before I became a mathematics major, and I remember studying acidity and the pH of a solution, and that uses logarithms. The pH of a solution is defined to be minus log base 10 of H+, where H+ is a measure of the hydrogen ion concentration. And this is measured in something called moles of hydrogen per liter. It ranges from 0, where your solution is very acidic, to 14, where it's very alkaline. So I'm not going to go into this application and use it, but if you're taking chemistry, you'll stumble across this formula, and now you'll know what it means. Logarithms. Here's another area of science where logarithms come into play. If you're a geology major, or if you are curious about earthquakes, you remember that there's a Richter scale, and the magnitude R of an earthquake of intensity I is given by the following formula. R equals logarithm base 10 of a quotient I over I sub 0. And here I sub 0 is called the benchmark intensity. It's the minimum intensity used for comparison. Intensity is kind of a measure of the wave energy of an earthquake. Again, I'm not going to use these examples in any more today, but if you're reading a geology textbook, you'll probably bump into this definition. Hey, and now you know what it means. Now, we have done some problems with interest rates, and these are a lot of fun, I think. We've talked about continuous compound interest and compounding n times per year. Let me look at a similar problem and use some logarithms to find an answer. Suppose you have a bank that pays 8% interest. Pretty good interest rate. So your bank pays 8% interest, compounded annually. Okay, so it's compounded annually. How many years would it take for your account to double, to say grow from $100 to $200? Let's answer this question. Okay, remember the formula. The amount in your account is equal to P, where P is the principal that you start with, the amount you deposit, times the quantity 1 plus R over N to the power NT. Now, who are these characters? Well, R is the interest rate, and you express it in decimal form, so 8% means 0.08. N is the number of compoundings per year, and for this example, it's just 1, and T is time. Good. So here's our setup. We start with $100. P is 100. We want to have $200, so the amount is 200, and we want to know how much time it takes. So we're trying to find T. And inside the parentheses, we have 1 plus R. Remember, N is 1 here. 1 plus 0.08. Well, we can simplify the 200 and the 100, and we have the equation 2 equals 1.08 to the T power. All right. And this is a very typical example of the power of logarithms. The variable which we're trying to find, T, is hiding up there as an exponent, isn't it? I want to bring it down to earth. How can I get that T downstairs? Well, take logarithms of both sides. Take the log of both sides of that equation, and I'll use natural logarithms. So the left-hand side is the natural logarithm of 2, and the right-hand side is the logarithm of 1.08 to the T power. And now use that property that the T can be moved into the front of the logarithm. And we have log 2 equals T times the logarithm of 1 plus 1.08. Divide, and you have T equals log 2 over log of 1.08, which is about 9 years. So it took about 9 years to double your money at 8% interest. Keep that in mind, because you might remember we talked about the rule of 70 for continuous compound interest. Well, there's also a rule of 72, which is much more common. And the rule of 72 is for interest compounded annually, as in the previous example. And what that rule says is, if you want to know the doubling time, take 72 and divide it by the interest rate. Well, in that problem, the interest rate was 8. 72 over 8, 9. Bingo, we got the answer a lot quicker. So the rule of 72 is a nice approximation technique for compound interest compounded annually. Great going. It was a nice application. Let's turn to having you be the teacher for a moment. So you're grading papers, one of my favorite activities, and a student turns in the following work. How would you grade it? And here's how the work goes. Student writes the log base 10 of 20, the log base 10 of 20 equals the log base 10 of the sum 10 plus 10. And then the student writes that's equal to log base 10 of 10 plus log base 10 of 10. And then the student says, oh, each of these is log base 10 of 10, that's equal to 1. And the next, so it's 1 plus 1, and 1 plus 1 is 2. So the final answer is 2. Student circles the answer. That's my answer, teacher. How would you grade it? Is that right? Is there a mistake here? Yeah, I hope you see it. The log of a sum, 10 plus 10, is not the sum of the logarithms. It's sad, but it's not. That's not right. That's the error. And in fact, if you use a calculator, you'll discover that log base 10 of 20 is really about 1.301. So it's not equal to 2. Sorry. Okay. This is a pre-calculus course. Let's look at an example, another example, from a real calculus text. So I opened up a calculus book and found this problem. Here was the problem. It said simplify the following expression. And the expression was the function f of x equals the natural log of a quotient. And in the numerator was x times the quantity x squared plus 1 squared, and the denominator was the square root of 2x cubed minus 1. So it's the log of a giant globular mass there, a really ugly thing inside that logarithm. Ouch. Let's rip it apart with our properties of logarithms. Well, the first thing you notice is we have the log of a product in the numerator, and then we have a division. So that's going to convert to the log of a sum and then a difference. Here we go. It'll be log x plus log of x squared plus 1 squared, and then minus the log of that denominator. And now wait, the square root symbol really means 1/2 power. So I can write it as minus logarithm 2x cubed minus 1. Good. And now we can do a minor simplification. Afterwards, we can pull those exponents into the front, and we get log x plus 2 log x squared plus 1 minus 1/2 log of 2x cubed minus 1. Great going. That was a nice application, I thought, of logarithms to calculus, and we saw the power of those properties. So let me take a little pause here and recap some of the most important ideas and features and properties of the exponential function and its inverse, the logarithmic function. And I'll focus on the natural exponential function, e to the x, and the natural logarithmic function, ln of x. Here are those graphs again. Y equals e to the x, and then the other graph is y equals log x. What are some of the features here that we can immediately pick out because of the inverse properties? Well, here's one. What's the horizontal asymptote of y equals e to the x? It's the x-axis, isn't it? So by symmetry, the vertical asymptote of the logarithmic function will be the y-axis, and you can see that in the picture. How about intercepts? What's the intercept of y equals e to the x? Well, it intercepts at the point 0, 1. Well, if 0, 1 is on the graph of e to the x, that means 1, 0 is on the graph of y equal the natural log of x. You see that symmetry again across the line y equals x. How about domains and ranges? What's the domain of the natural logarithmic function? X bigger than 0. Why is that true? Well, what's the range of its inverse? It was all the numbers above the x-axis, greater than 0. So domain and range interchange when you do inverse functions. Great, so really important graphs. I hope you savor them. Let's spend a little time maybe doing a different kind of question. I've put these questions on tests as a teacher. I'll sometimes give, say, 3 functions and ask the students to see if any of them are equal to each other. Here's how it might go. You might have the function f of x equal log of the quantity x over 2, and then you might have the function g of x equal log of x divided by log of 2, and how about the function h of x equal log of x minus log of 2? Are any of these functions identical? What do you think? Oh yeah, the first function and the third function are the same by that logarithmic property that the log of a quotient is the difference of the logarithms. That second function is not equal to either f or h. Here's one more problem, and this kind of has an interesting pedagogical twist to it. Suppose you're doing an exercise and your answer is log of the square root of 8. And then you turn to the back of your textbook and you go, ay. The textbook says the answer is 3/2 log 2. And you have a different answer, it looks like. You have log of the square root of 8. Textbook says 3/2 log 2. Help! Well, it turns out you're right. It's the same answer. Watch. The log of the square root of 8 is nothing more than the log of 8 to the 1/2 power. So you can pull the 1/2 out to the front. And now what about 8? Well, 8's 2 cubed. So it's 1/2 log of 2 cubed. So now the 3 can motor out as well, and you're left with 3/2 log 2. Wow, those are a lot of different expressions for the same answer. And in textbooks, you might have a different version of your answer. Don't just immediately assume you're wrong. You're probably right. It's just you have to do some manipulation to make your answer look like the textbook answer. And by the way, neither one is preferred. Okay, great. I thought we covered a lot of material today, a lot of properties of logarithms, including that important property that converts products to sums. Next time, we'll use a lot of these properties and start solving logarithmic equations and equations involving exponents. One of the most important tools will be what you saw a little bit earlier, pulling an exponent down to earth using logarithms. So I look forward to next lecture when we study equations involving logarithms and exponents. Thank you very much.